And why we're talking about the mindset? So when I did my undergraduate back in the late 1990s, I was taught programming, classic programming, using classic programming languages, C, C++, Pascal, and a bit of assembly language as well. And fast forward to 2015, when I did my first machine learning project. When I got, it's not REEXM, it's something else. And by that time, I had already forgotten about programming, about coding, all that sort of stuff. So it was a good opportunity to learn again. And this is when I heard of R for the first time. And at first, R seemed to me very awkward, for someone who's accustomed to classical programming languages. It felt strange, very slow, and I even wondered why R was even developed in the first place. It did not make any sense. What I failed to realize then is that I was looking at R from an incorrect perspective, from a programmer's perspective. Allow me to elaborate on this. So if you are a programmer, imagine you are a programmer. You deal with, you write programs, essentially. Your input is typically a problem, and it's your boss will tell you what to do this and that, and that's your input. So you have to figure out how you can solve this problem. What is your process? You write code mostly. Maybe there is little input usually, but mostly it's code manipulation. What is your output is a solution to that particular problem. And of course, when you write code, you make errors, you make mistakes. So you need to debug. Typically, you debug your syntax, where you forget semicolons here, add extra space there, etc. And also the semantics. Classical example, if you have a double equal sign for assignment instead of single, for comparison instead of single equal sign for comparison. Yeah, single for assignment, double for comparison. Programming languages typically use C, C++, Java, there is a whole bunch of them. But if you are a data scientist, your input is not going to be a problem. Mostly it's going to be data, and lots of data. That's what you are going to deal with. And your process, of course, you write code, but your code is not going to solve a problem directly, but is going to manipulate data, and it can be huge sometimes. Your output is also data, typically. Maybe your input is a bunch of data sets from different sources. You clean them, you merge them, you do whatever you do. And then at the end, you have a very clean, coherent data set that can be used maybe for machine learning. Of course, you still have to write code, so you will need to debug syntax and semantics, but also you need to debug data. What this means is that data can contain error, especially if you deal with data from external sources. Sometimes you have text where numerical values are expected. Sometimes you have missing values in A's. In A's are not zeros. Or you could have zeros where there shouldn't be. So you have, or you get division by zero error. So it's a little bit more complicated. And for programming languages, well, typically R, Python, Spark, there are specialized programming languages really designed for data science. And let's take an example, and let's say we want to calculate the distance between maybe Brighton Pier, for example, and 1 million postcodes in the UK. That's a lot, right? 1 million postcodes. To do that, we use a Haversine formula, and it looks something like this. But don't worry if this looks gibberish, because in R, it can be simplified and in a function, and it can look something much, much simpler like this. So I don't understand the formula itself. Someone figured it out. We just have to use it. And so let's do some code now. So I'm going to do a live demo. So fingers crossed, everything is going to be all right. So what we have here is very simple R code. It's going to load some libraries, and it's going to load the data set called NSPL. This is National Postcode Lookup file. It's from Office for National Statistics, I think. So essentially, this data set, this file contains all the postcode in the country, I think about 2.6 million postcodes, and it will also have their longitude and latitude, their coordinates. With the coordinates, we can then calculate the distance. I'm loading the region because I want to restrict the data set so that only England postcodes will be used. So what I will do is, I'm not going to do a million now. Okay, I will limit the sample to 75,000 postcodes. So let's see how this works. I'm just going to load this. Hopefully everything is going to be fine. Yes, it's loading. It will take a few seconds, and here we go. The dataset has been loaded. We can take a look at it here. So we have the postcode, the longitude, and the latitude. So if you were a programmer, what would you do? You would write a for loop to go through all these postcodes one by one, and in the loop body, you are going to do or to get the distance. So we have defined a function, the hover sign, just I have shown you earlier. This function will be called in every iteration. So obviously we are going to do 75,000 iterations here. So let me just highlight the code and let's run it. And while it's running, what I'll do is, I hope you can see my task manager here, and you can see some utilization. I see 50%, but it's probably that is Zoom. We are interested in R itself, and if we look at R, it's going to, I think, take about 12% utilization or so. That's my R session, and it's only 12%, which means it is single-threaded operation. A typical for loop is always single-threaded. I think 40 seconds or so have passed, and it's still running. It's still haven't finished. So maybe we'll give it a few more seconds, and we'll see. When it finishes, then we can validate the result. We can, just to make sure that we got the calculation. So essentially, this loop is going to calculate the distance, and it will automatically add a new column. It's going to call that column distance for loop. It should be almost finished by now. And yes, 47,000. I think it's taking even longer than I expected. Maybe because there is more utilization. Anyway, we can monitor and see 53,000. It's going to take a bit more, and it will finish. And it's interesting to see that's always utilizing almost 12%, which is 1/8 of this microprocessor, which has 4 cores and 8 threads. So let's see again, it's 69,000. I think we are almost there. 72,000. I'm watching this. This is the iterator here. And there we go. Finally, it's finished. And yeah, it took quite a bit of time, 104 seconds. That's way too slow. And that's why that was my first impression of R. It is extremely slow. If you write this in C, for example, it will finish in no time. And let's try something else now. We know the for loop, the programmer's favorite, is not good. R has some other functions. There are other iterators for each library, for example. That's another loop, and we can try to do the same thing. And by the way, if I watch the data set, we can see the new column distance for, that's a for loop, and we can see distances in meters. It seems fine. I'm going to run this. I promise you it will be quicker. But if we watch the task manager again, we can see the same thing, about 12% or so utilization, which means it's also a single-threaded operation. This one is going to be faster. Yeah, it has finished already, and that took 17 seconds. So R has some tools under its sleeve that can help us do the work faster. If you notice, I only use a single processor. How about if we do multi-threaded? So the for each loop can actually utilize more than one processor to do this. And before I start, I want everybody to try to guess how fast this will finish the job. So the normal single threaded talk about, all right, 4 seconds. You'll be surprised. So let's run this and see what's happening again. This will create a cluster in machine cluster, and it will distribute the workload. And so we can see our scripts here. They are doing some work. Utilization should be much higher now, 70% or so, which proves that, yes, it's actually using different threads. And it still hasn't finished. I know this will surprise many. And it's now done. And it took actually 26 seconds. So it even took longer. Counterintuitive, I know. I'll explain why this happens. But before I do that, I'll do one more try. And let's just verify that the other loops, the for loops, actually work. We can see the validation here, 500 meters and so, which means it really worked. It did the same thing. The last thing I'll do is what I call the R's way. So if you notice, there is no loop to begin with. There's no for loop, no iterator whatsoever. It's just a single line, even very elegant, very short. This time, I'm not going to monitor the performance, the time, and the reason is, by the time I click on run, it had already finished. In fact, it took actually less than 0.01 seconds. Did it actually work? So it should create a new column called distance R. And if I just look at the data set here, we can see it. And yes, indeed, it actually finished. So why the heck happens? So the first typical for loop took over 100 seconds, while the mutate function took a fraction of a second on the very same computer. Something doesn't add up. And I think I owe you an explanation here. What actually happens is, before I do that, by the way, I did the same code for 1 million postcodes. And if you notice, the classical for loop, it gets exponentially slower with larger data sets. Indeed, it took 8 hours. And the do loop, the single threaded, took much less. The multi-threaded took a bit more, but still nowhere close to the for loop. Interestingly, the mutate function still took under 1 second. And if this doesn't look real or doesn't sound real, what I'll do is I'll simply delete this line. I'll just reread the same data set. And I'm going to do it for, 2 million postcodes, I think. Let's see. The data set is now, we have 2.2 million postcodes. Let's go to the mutate and let's run this. And I think I just need to, yes, I need to probably, no, it's fine. I thought I'll need to remove that column. It's already removed. So let's run this again and bam. It took 0.43 seconds, less than 1 second, and it indeed finished. As you can see, it already finished. So the reason this is way faster is just because how I'm using our data table, and how our data table is stored in memory makes all the difference. In a typical relational database, these are called row oriented. So in memory, you have the first row followed by the next row, followed by the third row in memory, because in memory, you can't have rows and columns. You only have one long stream of data. So the way relational databases are stored in memory is in a row fashion. However, in an R data table, they are stored in a column-oriented fashion. So you have the first column, in this case, it is the postcodes, followed by the next column, maybe the longitude, then the latitude, and so on and so forth. What this means is this opens opportunity for something called vectorized memory access. So if you notice, the mutate function did not even need a loop, because what it did, it loaded, as long as you have enough RAM, of course, on your computer, it has loaded the first column, and which is a longitude, and then it hard loaded the second column, the latitude. And then there's one more thing, because new or recent microprocessors support a function called SIME. It's single instruction, multiple data. These features allow the processor to perform the same operation, if it is the same operation, on multiple data points, which means although it is single threaded, it actually done the work in parallel for us. And this is why it was so fast. Unfortunately, when I was, starting with R, I did not understand any of this. And I started to write lots of loops to do my work. And God, every time it took hours. And then I learned the hard way that it's not R's fault. It was my fault. I did not learn R the right way. I did not approach it in the right way. So ultimately, I think R as a programming language is very elegant. Sometimes you don't even need to write loops. It is very efficient, and it is blazingly fast as long as you know how to use it. I thought this makes a lot of sense. And if anybody tells you R is slow, R is bad, R is this and that, you say, maybe you are not approaching R with the right mindset.